We live in a world of continually varying analog dimensions. Sight, sound, temperature, voltage, current, as well as most physical and electrical parameters are perceived as changing in a continuous manner. As you are already aware, the analog signal has an infinite number of values. Even though our real world consists primarily of analog signals, they can be difficult to manipulate. Digital signals, on the other hand, can be controlled by simple logic circuits. Complex operations are more easily performed through the use of digital circuitry rather than analog systems. However, there comes a point in time when we must interface the digital world with the analog world. This is accomplished through the use of converters. The two basic converter circuits are the digital to analog converter and the analog to digital converter. In this video, you will learn basic techniques used for converting digital information into analog information, as well as how to convert from analog to digital. We will begin by first examining the digital to analog converter. Digital to analog converters are used to translate binary words from computers or other digital circuitry into proportional analog voltage levels. DA converters are used to drive analog devices such as meters, motor controllers, audio circuits, or perhaps even video circuits. Before discussing the techniques used for digital conversion, we will examine some common terms and definitions. The first term we shall define is the resolution. The resolution of a digital to analog converter is the number of discrete digital states that are used to express an analog signal. The resolution is directly related to the number of input bits which form the binary word. For example, a 4-bit DA converter contains 4 input bits. Therefore, it has a resolution of 4. The number of distinct and differing analog output levels the IC is capable of generating will be 16 levels. This was calculated by multiplying 2 to the 4th power, or 2 times 2 times 2 times 2. What this means is that the analog output of the 4-bit DA converter can be represented by up to 16 voltage levels. An 8-bit DA converter, on the other hand, can provide an analog output with up to 256 levels. Again, this was calculated by multiplying 2 to the 8th power. As you can see, the resolution of the output signal has been greatly increased. A 12-bit DA converter can represent an analog output with a resolution up to 4,096 distinct and different output levels. It should now be evident that the higher the bit level, the more accurately the analog signal will become. The next term we shall examine is the settling time. The settling time is a DAC term used to express the amount of time required for the analog output to stabilize after the digital input has changed. The settling time is usually specified as the time taken for the output to stabilize within plus or minus 1/2 of the least significant bit of the expected value after the binary input changes. The settling time is directly related to the number of input bits and the full-scale output voltage. For example, if an 8-bit digital to analog converter has a 0 to 10 volt output range, then the least significant bit value would be approximately 0.039 volts. This was calculated by dividing the full-scale output voltage of 10 volts by the number of different analog output voltage levels available from the device. As you saw earlier, the 8-bit DA converter is capable of generating 256 distinct and different voltage levels. Since the settling time is the time required for the output to stabilize within plus or minus 1/2 of the least significant bit value, then we must divide the 0.039 volts in half. Half of this value is 0.0195 volts. Therefore, the settling time would be the time required for the output to reach 0.0195 volts of the expected value. The settling time is typically under 10 microseconds. The next term we shall examine is the accuracy of the DA converter. The accuracy of the digital to analog converter represents how close the actual analog output is to the expected output. The accuracy is usually specified as being either plus or minus a given bit value. This bit value may range from 1/2 the value of the least significant bit to 2 times the least significant bit value. For example, let's assume that a DAC device has an accuracy of plus or minus 2 bits. We will also assume that it is an 8-bit DA converter with a 0 to 10 volt analog output. This places the least significant bit value at 0.039 volts. Therefore, for any binary input, the output voltage may be higher or lower than the expected value by 2 times the value of the least significant bit. If the expected output value is 5 volts, then the actual value could range from 4.92 volts to 5.08 volts. If this same device has an accuracy of plus or minus 1/2 bit and the expected output is 5 volts, then the actual output voltage would only range from 4.98 volts to 5.02 volts. As you can see, the smaller the accuracy value, the more closely the actual output will match the expected output. The final term we shall examine is the monotonicity. As you shall soon see, the analog output voltage of a digital to analog converter will progress in steps as the binary input word increments. In the ideal situation, each increment in the binary word input will cause a known predictable step in the output voltage. However, there are devices in which the switching and amplifier components do not allow enough current to flow under all input conditions. This causes the device to skip steps at certain bit levels. While the monotonicity problems of a low binary bit value may have little effect on the output, this effect becomes much more significant as the weight of the bit increases. The DAC device is said to be monotonic if it does not miss any of the steps across the entire range of the binary inputs. Before we start the discussion of the techniques used for data conversion, there are certain signals that you will encounter which need defining. This will allow you to understand the function and limitations of the various types of circuits more clearly. Here you see the basic analog signal. The analog signal contains an infinite number of voltage or current potentials. Even though there are limits imposed on the permissible ranges to which the analog signal may exist, the signal can take on any value within that set of limits. For example, one of the limits might be in the unit of time where 0 is the turn-on point, and all units to the right of 0 would indicate a specific period of time. Another limit could be in the magnitude, used to indicate the values of current or voltage. In certain situations, the low-end limit could be 0 volts, with all units above the low-end limit indicating voltages higher than 0 volts. As you can see, the analog signal may have any value within this limit range. We could also set the limits to include both positive and negative potentials. This would allow the indications of voltages or currents to become displayed as being either above the 0 reference line or below the 0 reference line. Here you see a sampled signal. If an analog signal is allowed to exist only at certain discrete instants in time, a display such as the one being shown to you now will show the instantaneous values of the measured signal. The magnitude of the individual signals can represent any value within the imposed limits. The time limit of this signal might be measured in milliseconds or microseconds. If the time limit was marked off in units of milliseconds, there could be up to 1,000 samples per second. There is, however, a drawback in sampled signals. For example, if the analog signal is not sampled often enough, you will lose the overall wave shape of the signal. Now that you have seen some of the characteristics of the analog signal, we will return to the digital to analog converter. In the discussion of the digital to analog converter, we will assume that the binary numbers are in an 8-bit format using straight binary coding, which follows the binary notation numbering system. As you recall, the numbers raised by a power of 2 each time the most significant bit is moved one place to the left. There will also be times within the video when the BCD format will be used. Earlier it was mentioned that a digital to analog converter circuit would produce an analog signal which is proportional to its binary word input. However, this is only partially true. The DA converter circuit will produce an analog signal which is proportional to both the binary word input and its reference signal. The reference signal is a stable precision reference source that supplies power to the current sources within the device. The binary weighted ladder and the R2R ladder configurations are the two most common types of digital to analog devices now available. Both are based on current output resistor ladders. Here you see the basic binary weighted ladder DA converter circuit. Notice that it uses a simple operational amplifier with resistor feedback. It also contains a group of resistors and switching devices which can place the resistors at ground potential or at the reference voltage level. Notice that the resistor values change according to the binary system. As the resistors go from right to left, they double in resistive value. Therefore, the resistor labeled 8R will be 8 times larger in value than would be resistor R. Since resistor 8R allows the least amount of current to flow, it is designated as the least significant bit. And since resistor R, on the other hand, has the smallest resistive value, it will allow the most current to flow. Therefore, it is designated as the most significant bit. The accuracy of the DA converter circuit will depend on the precision of the reference source as well as the precision and stability of its components. Resistors, as you are already aware, change with time due to aging and variations in the ambient temperature. We will now examine a simple DA converter circuit to see how it works. Notice that this circuit consists of 8 resistors in a binary weighted ladder configuration. Each resistor is connected to a switching device which can place the resistor at ground potential or at the reference source potential. When the switch is at ground potential, no current is allowed to flow through that particular resistor. However, when the switch is moved to the reference source, a current is allowed to flow into the input of the operational amplifier. This results in the amplifier producing an output proportional to its input voltage derived from the ladder output current and the feedback resistor. As you can see from the functional table, the analog output will depend upon the sum of the inputs being applied across the ladder resistors. The full-scale output voltage of this circuit is 10 volts, and the binary input code of this circuit is in the BCD format. As you recall, the BCD format only allows digits 0 through 9 to be expressed. Therefore, the percentage of full-scale voltage represented by this circuit can only be 99%. Since this circuit generates an analog signal of one polarity only, it is often referred to as a unipolar digital to analog converter circuit. There are, however, DAC circuits which produce analog outputs in both the positive and negative sign. These circuits are often referred to as bipolar digital to analog converters. The bipolar digital to analog converter circuit uses 2 reference sources. One is positive and one is negative. A sign bit is used to control which reference source is to be switched in for a given input code. Notice that when the sign bit is 0, the output is positive going in its transition, and when the sign bit is 1, the output swings negative. The binary weighted resistor ladder circuit, however, does have problems if the bit length is longer than 8. This is due to the fact that the resistor values become much too large. For example, if resistor R is set to 10,000 ohms, then resistor 128R must be 1.28 million ohms, since it is doubled in value 7 times. Consider what happens when the reference voltage is plus 10 volts. Ohm's law shows that the current flow through resistor 128R will only be 7.8 microamps. Finding operational amplifiers that respond to input currents of this level becomes difficult unless cost is no object. In most lower-cost devices, the least significant bit current will be so low that the op-amp device will not produce a change at the output. Similarly, if you try to extend the range by making resistor R smaller, you would encounter exactly the opposite problem. As you can see, we have made resistor R 100 ohms. When we apply Ohm's law to calculate the current flow through resistor R, we see that the current flow will be 100 milliamps. This is more than most operational amplifiers can safely handle. The solution to this dilemma is to use the R2R ladder configuration. Here you see the R2R ladder configuration. It derives its name from the fact that the ladder consists of only 2 resistive values. These are the basic resistive value and a value of twice that amount. Most commercial digital to analog converter circuits will use the R2R ladder technique. Notice that this circuit also uses a feedback resistor placed between the output of the op-amp and one of its inputs. Without this feedback resistor, the op-amp would function as a comparator device instead of as an amplifier. The R2R ladder configuration also contains a group of resistors and switching devices designed to place the resistors at ground potential or at the reference source level. Since the 2R resistor furthest from the reference voltage source has the least amount of current flowing through it due to the other series R resistors, it is designated as the least significant bit. And in the same respect, since the 2R resistor nearest the reference voltage source has the highest current flow through it, this resistor is designated as the most significant bit. The basic operation of the R2R ladder network is very similar to its counterpart, the binary weighted ladder network. Here you see an 8-input R2R ladder DA converter circuit. The input data is in the BCD format. As was mentioned previously in the binary weighted ladder configuration, the highest possible percentage of output from this circuit is only 99%. The amount of current flowing into the input of the operational amplifier will depend upon the binary word input as well as the feedback current from the feedback resistor. The more current which flows into the input of the op-amp, the higher the output voltage will become. The R2R ladder configuration allows a much higher precision of digital to analog conversion since all the inputs carry comparable currents. The ideal digital to analog converter device should deliver a 0-volt output when the digital word is 0. However, due to the input offset of the operational amplifier contained within the device, a small voltage may be present at the DA converter's output. When all the inputs are a logical 1, the output should be approximately 99% of the full-scale output. When the reference voltage is 10 volts, the output should change at a rate of 39.215 millivolts for each 1-bit increment. For example, a binary input of 11001000 would cause the DAC device to produce an output of 7.843 volts. This was calculated by multiplying the decimal equivalent of the binary input times 0.039215 volts. A binary input of 100000001 would cause the device to produce approximately 5 volts at the output. Or a binary input of 000111011 would cause the DA converter to produce approximately 1 volt at its output. As you have seen, the output of the digital to analog converter circuit will depend upon the reference voltage and its binary weighted input. Digital to analog converter circuits are used extensively in today's modern industrial equipment. Before continuing this video, we will review some of the important concepts covered thus far. The digital to analog converter circuit is used to change digital quantities into a voltage or current whose magnitude is proportional to the binary input and reference voltage. The two basic types of DA converters are binary weighted ladders and the R2R ladder networks. Both are based on current output resistor ladders. The digital information placed at the inputs of the digital to analog converter may be in straight binary or in the BCD format. The resistors in the binary weighted ladder configuration double in value as they go from the most significant bit to the least significant bit. The unipolar DA converter will generate an analog output of one polarity only. The bipolar DA converter, on the other hand, will generate an analog output capable of both positive and negative output signal levels. The binary weighted ladder network is typically limited to 8 binary inputs. This is due to the fact that the value of the least significant bit resistor becomes too large, thus not allowing sufficient current to flow into the op-amp to facilitate a change at the output. Because of this limitation, the R2R ladder configuration is the most widely used of the two. The input resistors in the R2R ladder network consist of only two resistive values, the base resistive value and a value of twice the base value. The R2R ladder configuration is a much more precise digital to analog converter device since all the inputs carry comparable currents. Since the output of the DA converter is limited by the number of binary inputs, it cannot represent an infinite number of output levels. Instead, it produces an output which increases in steps according to the binary input. The resolution of a digital to analog converter is the number of discrete digital states that are used to express an analog signal. The settling time of a DA converter is the amount of time required for the analog output to stabilize after the digital input has changed. The accuracy of the DAC device represents how close the actual analog output is to the expected output. This is usually specified as being plus or minus a given bit value. The DA converter is said to be monotonic if it does not miss any of the steps across the entire range of binary inputs. This concludes review number 1. So far, we have discussed the basic operating principles of two of the most common types of digital to analog circuits being used today, the binary weighted ladder and the R2R ladder. Next, we shall examine a common DA converter device. Here you see the DAC08 integrated circuit. It is an 8-bit current output digital to analog converter IC. Internally, this device contains the R2R ladder network, electronic switching devices, current sources, and a reference amplifier. Notice there are two current output terminals. One is the true output and one is the complemented output. The true output will increase from 0 to full scale as the input increases from hexadecimal 00 to hexadecimal FF. And the complemented output will decrease from full scale to 0 as the digital inputs increment over the same range. The DAC08 device can operate at frequencies up to 1 MHz and requires a DC power supply voltage of typically 12 to minus 15 volts. Here you see a basic circuit where the DAC08 is being operated in a positive unipolar configuration. Notice there are two power supply connections required for this device. One goes to a positive DC power supply, while the other goes to a negative DC power supply. Also notice that each power supply terminal is bypassed to ground through a 0.1 microfarad capacitor. The compensation input is used to form the AC frequency response properties of the circuit. In most TTL applications, the compensation input will be bypassed to the negative DC power supply through a 0.01 microfarad capacitor. The reference inputs, as you saw earlier, are fed into the inverting and non-inverting inputs of the internal operational amplifier. In most cases, the reference resistors will be of equal value. The values of these resistors are chosen to set the level of the reference current. When used in TTL applications, these values will typically be about 5,000 ohms. The terminal, labeled VLC, is the threshold voltage terminal, which controls the high-low voltage levels recognized by the digital input terminals. This special feature allows the DAC08 device to become compatible with most digital logic families. This device can also be operated in a negative unipolar configuration. This is achieved by connecting the resistor feeding the positive reference input to ground, then connecting the resistor feeding the negative reference input to the negative current reference source. The resistors used at the reference inputs should always be a low temperature coefficient, high precision device for best overall operation. The output current of this device can also be adjusted by varying the reference input current. This allows full-scale output calibration capabilities. This is accomplished through the use of a balancing circuit. Notice that a 4500 ohm resistor is placed at the positive reference source of the device. Also notice that a 50,000 ohm potentiometer is placed between the positive reference voltage source and ground, with the wiper being connected directly to the negative reference voltage input. This pot should be adjusted so the negative voltage reference input sees about 5,000 ohms to ground. It is necessary to keep the reference current as precise as possible, since the output current is directly proportional to the reference input current values. Fluctuations of the input currents will result in errors at the output. Since the reference currents are so critical, it is necessary to use only a reference type power supply source. The negative or positive power supply voltages should never be used as the reference source. To this point, we have only considered the DAC-08 device as a current source at the outputs. However, there are applications when a voltage output operation is required. This can also be provided with the DAC-08 device. By simply placing resistors at the outputs of the digital to analog converter device and using the voltage drops across these resistors, you can create an output voltage potential. The resistors are used as pull-down devices since the output current flows through the resistors to ground. To better illustrate how this circuit works, we will assume that the DA converter device has an output which varies from 0 to 10 volts full scale. The output current must therefore be 2 milliamps. This was calculated by dividing the output pull-down resistor value into the full-scale voltage of the device, which was stated as being 10 volts. With an 8-bit input, there are 256 individual binary increments available with this device. Since one of the binary states must be 0, this only allows 255 states in which the output may increment from the least significant bit to full scale. When we divide the full scale voltage by the number of increments available to reach full scale, we see that each bit will increase the output by approximately 39.2 millivolts. When a binary input of 00, 01, 10, 01 is applied at the inputs of this device, we see that the analog output becomes approximately 980 millivolts. When the binary input is changed to 10, 01, 01, 10, then the analog output changes to approximately 5.88 volts. And by making all the inputs high, we can produce an output voltage of approximately 9.99 volts. Now let's see what happens to the DA converter device as its complemented output when these same inputs are applied. When binary input 00, 01, 10, 01 was applied, we found that the DA converter device produced a positive 980 millivolts at its true output. But as you can see, the complemented output with this same binary input is approximately 9.02 volts positive. This is due to the fact that the complemented output will decrease in value as the binary input increases in value. In other words, the complemented value will decrease from full scale to 0 as the binary input increases. To calculate the complemented output, you simply convert the binary input into its complemented form, then multiply the decimal equivalent of the complemented number times the voltage value of a single bit. When binary input 10, 01, 01, 10 was applied at the binary inputs, you saw that the true analog output was approximately 5.88 volts. As you can see, the complemented output with this same binary input is now approximately 4.12 volts positive. And when all the data inputs were high, you saw that the true analog output was approximately 9.99 volts. As you can see, at the complemented output, the voltage is now 0. Next, we will examine the analog to digital converter. Many applications require that an analog input signal be converted to digital form for processing. This is accomplished with the analog to digital converter. The analog to digital converter, or ADC as it is sometimes called, is used to translate a continuous analog signal into a finite number of digital bits. The resulting digital word becomes the binary representation of the analog level at the instant it was converted. The resolution of the ADC is very similar to its DAC counterpart, in that it is the number of bits with which the ADC can represent the analog input signal. For example, an ADC with 4 bits will have a resolution of 4 bits. This allows the device to represent the analog input signal with up to 16 binary words. In simpler terms, the analog input signal may be represented by 16 separate instantaneous values for each sample of the input signal. An 8-bit ADC, on the other hand, can represent the analog input signal with up to 256 discrete words. This allows each sample of the input signal to be broken down into 256 separate values. And a 12-bit ADC can represent the analog input signal with up to 4,096 individual binary words. As you can see, the more bits of resolution the ADC can provide, the more accurately it will represent the analog input signal. Conversion time is another important aspect of the analog to digital converter. The conversion of the analog signal is a precise, deliberate process, and as a result requires a certain amount of time to sample the input signal, digitize the input signal, and make the binary results available at the output. The conversion time is the period of time required to complete this process. Conversion times may range from microseconds to milliseconds. Since the analog to digital converter requires a finite amount of time to perform a conversion, there can only be just so many samples of the input signal in which the converter can digitize in any given time period. This is called the sample rate. For example, let's assume that an ADC can make one conversion in 1 millisecond. Theoretically, the ADC will make 1,000 conversions in 1 second. With a sample rate of 1,000 conversions per second, a 1 Hz signal could be represented with 1,000 binary words. This would result in a very good representation of the actual analog input. However, if the input signal had a frequency of 10,000 cycles per second and the AD converter had a conversion time of 1 millisecond, then the input signal would only be sampled once every 10 input cycles. This clearly would not work. The minimum that an analog signal may be represented is in 2 parts. For a simple sine wave signal, this may be acceptable, but as the signal becomes more complex, the 2-part representation will not work. Therefore, the number of times the signal is sampled must be increased. If a sample rate of 8 points per cycle were used, then a sample rate of 8 times the input signal frequency must be used. For a 10 kilohertz input signal, the sampling rate would be 80,000 times per second. This means that the AD converter must have the ability to convert a sample of the input signal in 12.5 microseconds. Even though this is extremely fast for most AD converters, there are devices on the market which have conversion times which can approach 1 microsecond. If the analog to digital converter cannot sample the input signal fast enough, the information contained in the analog input will become lost. The quantizing error is another important characteristic of the AD converter. The quantizing error is a result of the changes in the analog input level during the conversion process. As you recall, a specific amount of time is required for the ADC device to convert the analog input into a digitized output. This was referred to as the conversion time. If the input level changes during the conversion, the binary output will represent the voltage level at the end of the conversion time instead of at the beginning. The faster the signal changes, or the higher the slew rate, the greater the quantizing error will become. One common method used to reduce the quantizing error is to use a sample and hold circuit at the input of the device. This simple sample and hold circuit can be used to eliminate the effects of quantizing error. Let's examine this circuit to see how it works. The electronic analog switch, which is controlled by a clocking pulse, closes to take a rapid sample of the analog input signal. Capacitor C1 will then charge to the potential of the voltage present at the input. The charge on the capacitor is monitored by the unity gain amplifier. This op-amp should have a very high input impedance. When the analog switch is released, it returns to its off or hold position. This results in capacitor C1 becoming disconnected from the input source. Because of the op-amp's very high input impedance, the charge stored on capacitor C1 is effectively trapped and the voltage across C1 will remain almost constant for an appreciable amount of time. The unity gain amplifier then transmits this instantaneous voltage level into the input of the analog to digital converter. As you can see, by using a sample and hold circuit at the input of the AD converter, the quantizing error has been greatly reduced or completely eliminated. This is due to the fact that the input voltage to the ADC stage remains constant during the conversion time period. We will now pause for a short review of the most recently discussed material. The analog to digital converter circuit is used to convert an analog signal into a digitized output. The resolution of the AD converter is the number of bits with which the ADC can represent the analog input signal. A 4-bit ADC can represent the input signal in 16 separate instantaneous values for each sample of the input signal. An 8-bit analog to digital converter will represent the input signal in 256 separate values. And a 12-bit ADC will represent the analog input signal in 4,096 individual instantaneous values. As you can see, the more bits of resolution the AD converter can provide, the more accurately it will represent the analog input signal. The conversion time of the AD converter is the time required for the device to sample, digitize, and produce the digitized results at the output. The sample rate is the number of times the AD converter is able to examine the level of the input signal. The sample rate must never drop below 2. The quantizing error of the ADC is a result of the changes in the analog input level during the conversion process. The higher the slew rate, the greater the quantizing error will become. Sample and hold circuits are commonly used to reduce the quantizing error effect. This concludes review number 2. Next we will examine some common analog to digital converter techniques. A variety of methods have been developed over the years to perform the digitizing of analog signals. You will examine 4 of these techniques in this video. Here you see a single-slope integrator analog to digital converter circuit. The single-slope ADC is sometimes used in the less expensive digital panel meters and digital multimeters. The single-slope integrator is a simple design that is limited to applications which can tolerate an accuracy of only 1 to 2%. The single-slope integrator AD converter consists of 5 basic sections. The first section is the ramp generator. The ramp generator consists of an op-amp with one input connected to a stable, fixed reference voltage source, while the other input is tied to ground. The reference source causes the input reference current to remain essentially constant. This results in the voltage at the output of the op-amp to rise in a nearly linear manner, creating the voltage ramp. The second section is the comparator. The comparator is merely an operational amplifier with no external feedback loop. If you recall, when an op-amp is used with no feedback from the output to one of its inputs, the device will essentially operate with its open loop gain. This causes the op-amp to switch from cutoff to saturation, or from saturation to cutoff, in a very short period of time. Basically, the op-amp works as a switch and is not linear. The third section of this circuit is the logic section. The logic section consists of the 3-input AND gate and the main gate generator. When the output of the main gate generator is low, switch 1 will remain closed, which results in the ramp voltage being 0. The frequency of the main gate control is equal to the sampling rate time. When the output of the generator goes high, switch 1 opens, which allows the capacitor to charge. This causes the ramp voltage to rise in a linear fashion. The fourth section is the clock. The clock is used to control the output of the 3-input AND gate. The clock frequency will be much higher than the frequency produced by the main gate control. The fifth and final section is the output encoder circuit. As you can see, the circuit being illustrated uses an 8-bit serial in, parallel out binary counter and a parallel in, parallel out shift register latch. The binary counter will see a pulse train of digital pulses with a length proportional to the amplitude of the analog input voltage. The maximum count of the encoder stage should be proportional to the maximum range of the analog input signal. Now let's examine the operation of this simple circuit. When the output of the main gate control circuit is low, switch 1 will remain closed. This results in the ramp voltage remaining at 0. The frequency of this circuit will determine the desired sampling rate time. When the output of the main gate control circuit goes high, switch S1 opens, and as a result, the ramp voltage will begin to rise in a linear manner. The output of the ramp generator is then fed into the inverting input of the comparator circuit. When the ramp voltage is equal to the amplitude of the analog signal being sampled, the differential voltage as seen by the comparator will drop to 0, which will cause the output of the comparator device to go low. As you recall from Digital 1 of the UCanDo series, the AND gate requires all inputs to be high before its output will go high. Therefore, while the comparator output is high and the main gate control is high, the 3-input AND gate will go high every time the clock pulse goes high. When the comparator goes low, the AND gate will turn off. During the period of time that the output of the AND gate is following the on-off transition of the clocking signal, it is feeding the binary counter with a series of digital pulses which are proportional to the sampled analog input signal. The sequence just described occurs 16 times for every cycle of a 4-bit ADC, 256 times for every cycle of an 8-bit ADC, and 4,096 times for a 12-bit analog to digital converter. There are advantages and disadvantages with the single-slope converter design. Some of the disadvantages found in the single-slope integrator AD converter are 1. The ramp voltage may be nonlinear. 2. The clocking pulses may be unstable over the conversion process. And 3. Certain noise impulses tend to cause errors in the ramp generator output voltage. The primary advantage of this circuit is its simplicity and low cost. Here you see the next AD converter design, which uses the dual-slope conversion technique. Many of the problems encountered with the single-slope integrator are corrected with the dual-slope integrator design. The principal sections of the dual-slope integrator converter are the integrator section, the comparator section, the main gate with its clock input, the counter section and output latch, the control logic section, the negative reference voltage or current source, and input switch S1, which is controlled by the control logic section. Also notice that the positive analog input is fed into switch 1 along with the negative reference voltage. When the start of conversion pulse is received by the control logic section, several things occur. 1. Switch 2 momentarily closes to discharge any residue voltage on capacitor C1. 2. A reset pulse is applied to the counter section to ensure that its starting state is 0. And 3. Switch S1 is connected to the analog in input. Notice that all these occurred at the same instant. When the positive analog input signal is applied, the output of the integrator section will ramp in a negative direction. This negative voltage will force the output of the comparator section high. The high output from the comparator section and the series of high clock pulses cause the main gate to produce a series of clock pulses into the counter circuit. This in turn causes the counter to increment. The counter is allowed to overflow and produce a carry signal, which is then applied to the control logic section. When the overflow occurs, the control logic section switches the integrator input switch S1 to the negative precision reference source. With the negative reference voltage now being applied to the integrator, its output will ramp back in a positive direction. This allows the integrator capacitor C1 to begin discharging. Because the reference voltage has a constant level, the slope of the discharge will remain constant, yet proportional to the analog input signal. After the overflow pulse, the counter begins a new series of counts. The counter will continue to increment until capacitor C1 has discharged and the integrator output drops to 0. When the integrator output reaches 0, the comparator output will go low, thereby shutting off the clock pulses to the counter. The count accumulated during this second series of counts will represent the instantaneous input voltage. After a predetermined amount of time, the control logic section will issue an end of conversion pulse to acknowledge that the data at the output is valid. In an effort to simplify the sequence of the dual slope integrator design, we will use this simple timing diagram. The first thing you should notice about this diagram is that the sampled input has a fixed time frame. You should also notice that the reference voltage has a fixed time frame as well. Here you see a low input signal being sampled. When the sampled signal reaches 0 in the fixed reference time frame, the clock pulses going into the counter section stop, which causes the counter to stop counting. The count accumulated during the fixed reference time frame will represent the sampled input voltage. Now you see a larger input signal being sampled. Notice that the sampled signal took longer to reach 0 than did the previous signal. The longer the signal takes to reach 0, the more clock pulses are fed into the counter circuit. The major disadvantage of the dual slope converter is the extended period of time required to make a conversion. The dual slope converter may require more than 50 milliseconds to translate a high input voltage. Next, we shall examine the parallel analog to digital converter design. Very few analog to digital converter circuits are as fast as the parallel converter. The conversion speed of this converter is so fast, it is often called a flash converter. The flash converter uses a bank of parallel comparators to process the analog input signal. One input from each comparator in the stack is connected directly to the analog input signal. The other comparator inputs are biased by a DC reference source through a simple precision resistor network. The resistor values are chosen so that each comparator is biased one least significant bit higher than the next one down in the chain. The maximum input voltage which can be converted will depend upon the value of the reference voltage used. Since the output of each comparator is either on or off, they become compatible with digital logic. With no input voltages, the output of each comparator is a logic low. As the input voltage increases, the output of each comparator, starting with the least significant bit, will cascade high as the input exceeds each reference voltage set by the voltage divider network. A network of digital gates which form a decoder network is used to convert the array of comparator signals into a binary word which is made available at the converter output. As you may have noticed, it takes 2n-1 comparators to support the resolution of this converter. As you can see, this simple 2-bit converter requires 2 to the second power minus 1, or 3 comparators, to support the 2-bit output. An 8-bit flash converter would require 255 comparators, and so on. The vast complexity of this design is one of the flash converter's biggest disadvantages. The major advantage of this converter is, of course, its speed. Since the analog input signal is applied to every comparator simultaneously, the conversion time is basically equal to the propagation delay of the comparators and the gating circuitry. Flash conversion can be accomplished in just a few microseconds. Next, we shall examine the successive approximation analog to digital converter. Of all the techniques that have been covered to this point, the successive approximation approach has become the technique of choice for the analog to digital converter. This is due to its low cost, moderate resolution, and high speed. The successive approximation converter operates by making several successive trials comparing the analog input voltage with a reference signal generated by an internal digital to analog converter. To simplify the operation of the successive approximation technique, we will first examine it in an analogy form using this simple balancing scale system. Notice that the weights are calibrated in powers of 2. There is a 1 ounce, 2 ounce, 4 ounce, and 8 ounce weight. We will begin by placing an unknown weight value on the scale. This unknown value will represent the analog input signal. When the trial weights match the unknown weight, the scale will become balanced. We will begin the measurement by placing the heaviest trial weight in the left-hand pan. If the trial weight is greater than the unknown weight, the balance will shift and the needle will swing left. But if the trial weight is less than the unknown weight value, the scale will remain tilted to the right. In this example, the unknown weight is greater than the heaviest trial weight, therefore the scale remains tilted to the right. Since the scale did not balance, we place the next heaviest trial weight in the left-hand pan. Notice that the balance of the scale shifted and the scale is now tilted to the left. Since the 4 ounce trial weight weighed too much, it was removed and the next smallest weight was applied. When the weight was removed, the scale would have shifted back to the right, but as you can see, when the 2 ounce trial weight was placed on the left-hand pan, the scale almost became balanced. To finish balancing the scale, we simply added the final and smallest of the trial weights. Once the scale became balanced, we simply added the total trial weight values to determine the unknown weight value. As you can see, the unknown weight value is 11 ounces. This same technique is used in the successive approximation approach when converting analog information into digital information. Here you see a block diagram of a successive approximation analog to digital converter. As you shall soon see, this converter circuit operates by making several successive trials comparing the analog input voltage with a reference voltage generated by a digital to analog converter contained within the device. This circuit consists of a comparator, a successive approximation register, a digital to analog converter, and an output latch. The conversion cycle begins when an analog input signal is applied to the converter along with the start of conversion pulse, labeled SOC, at the successive approximation register. The start of conversion pulse also resets the successive approximation register to all zeros. When the clock signal, which is fed into the successive approximation register, goes high, it turns on the most significant bit output. This in turn sets the output of the digital to analog converter section to 50% of its full scale output. The successive approximation register then looks at the comparator's output to see if the DA converter reference voltage output is greater or less than the analog input signal. If the reference voltage is greater than the analog input, the comparator output will be off. The successive approximation register will turn off the most significant bit and call it a 0. Or if, on the other hand, the DA converter reference voltage is less than the analog input voltage, the comparator will remain on and the successive approximation register will leave the most significant bit on and call it a 1. All of this is accomplished in one clock cycle. As the next clock pulse goes high, the successive approximation register turns on the second most significant bit and rechecks the results from the comparator. Once again, if the new DA reference signal is greater than the input voltage, the comparator output will be off, which results in the successive approximation register turning off the bit and calling it a 0. Or if the reference signal is less than the analog input signal, then the comparator output will remain on, which results in the bit remaining on. The successive approximation register will examine each bit in this same fashion, from the most significant bit to the least significant bit, until all bits have been examined. Since one bit is examined during each clock pulse, an 8-bit analog to digital converter using this technique will process the conversion in approximately 8 clock pulses. As you can see, after the least significant bit had been evaluated and processed, the successive approximation register sent out an end of conversion pulse which latched the resulting binary word directly to the output. Even though the successive approximation converter operation is more complex than the 3 previous converters examined, it is perhaps the most efficient type of AD converter presently available. As you have seen, this style of converter is capable of extremely fast conversions at high resolutions. When utilizing this technique, 12 bits of resolution can be processed in 10 microseconds or less. The field of electronics has virtually outgrown the human mind's ability to memorize and maintain the knowledge you gain while studying the various subject areas. Only by constant review does your mind have a chance to file and store away the information acquired during your studies. Constant reviews will assist you in being able to recall an amazing amount of valuable facts. UCanDo videos make these reviews timely and effective.